want to introduce today's speaker, RC Merc Mercure Jr. He is the chairman of Essentia Imaging, a company specializing in applying computational optics to real-world problems. He holds a PhD in physics from this university, and he has over 50 years of managerial experience in high-tech companies. He has helped found a number of companies, including the predecessor of Ball Aerospace, and also CDM Optics, CDM Optics. He has been the director in numerous companies, public and private, including three New York Stock Exchange companies. And in 2011, he received an honorary Doctor of Science degree from the University of Florida. So, welcome.
Thank you. Well, as you see, the whole idea of this presentation is to talk about the commercial aspects of computational imaging or sensing or computational optics. And the subtitle is what I claim it could be a new era in optics. It's not yet certain in my view that it will be, but it certainly can be. So I'm going to try as a goal here to show you that there are certain conditions that have to be met. They're necessary, but maybe not sufficient conditions that have to be met at a particular point in time for a particular technology to become successful in the commercial arena. And by that I mean successful in terms of the organization is viable, it makes money, it can sustain itself, it sells things, people derive value from it. You heard a speaker last week talk about the government marketplace for this. I'm not going to touch that. Today it's purely, I'm going to talk about the commercial aspects. And what I'm going to do to set the stage is to ask the question, how did we get where we are today from where we started? What can we learn from that? What are these conditions that allow that to happen? Then once I've set the stage and hopefully convince you that these conditions are real, we'll talk about commercial computational optics. Where are we today in terms of computational instruments that you can go out and buy? And then to finish up, I'll make some observations on what I believe is going to have to happen to allow this technology, this brand new technology, to really flourish, and a little glimpse into perhaps what's needed for the future. Show and tell time. Does anybody know what this is? Well, it's called a Nimrud lens. It was discovered by archaeologists in the ancient city of Nimrud in Assyria around 750 BC. It's a naturally occurring rock crystal. You can see it has a lot of blemishes in it. And 35 millimeters in diameter, 110 millimeters in focal length. It's hard to know exactly why this was. I think the two principal theories is one, it was either a magnifying lens or it was a burning lens. And by that I mean it concentrated the sun's rays to a spot that you could light fire with. And just as an interesting aside, later on, I think it's around 1100, archaeologists found in a Viking site aspheric burning lenses that were made by hand that could light a real fire. I mean, it was just not smoke, but it concentrated the sun so much that they could light fires bang. Now, what's this? Probably you know this one. Exactly. It's a Carl Zeiss photolithography lens working in 248 nanometers, or to us old guys, 2,480 angstroms, and has a resolution of less than 80 nanometers. It's a huge thing, as you can see with the guy standing by it. It requires special optics. I think this one is potassium fluoride, but I'm not sure. It would be a fluoride to have that light go through it. Incidentally, it can't have air in there. It has to have a gas that's transparent at that wavelength as well. It's the state of the art. I don't know how many lenses it has, but I'm going to guess upwards of 40, maybe even more. And the cost, I'm going to guess, is several $1 million. It might be even approaching 10 million, I'm not sure. But the point here is, in 3,000 years, we've come from somebody hacking at a naturally appearing crystal, a natural crystal, to something that is the state of the art of the optics industry. Now the question I want to discuss is why? What drove this advance? And I'll make an observation right off the bat that historically the practice of optics, classical optics, has been to produce the finest image possible on the focal plane with the constraints of cost and other constraints. But the optical designer over history has never had to worry about anything except controlling aberrations, etc., to produce this fine image. He never gave a damn about what happened afterwards. It was not in his purview. And that's a very important thing to bear in mind. Now I want to introduce to you what I call a driver, the concept of driver. This is not, original with me, but and I want to define this because this is kind of the whole essence of what I'm trying to get across. A driver is a resource, it could be physical, intellectual, or financial, that is required to be available at a particular time to enable a technology to advance commercially. And as I said earlier, these drivers, I believe, are necessary, but they may not be sufficient. So, I define what I call the M drivers, the alliterative M drivers. Methods, machines, materials, and markets and money. Methods encompass manufacturing methods, theory, and incidentally, I'm now going to truncate the time scale to the last four centuries, starting in the early 1600s. The theory, and Snell's law came about in the 1600s, middle, I think, 1600s, and design. How do you design lenses? What kind of tricks do you have? What kind of abilities do you have? The methods of design. Machines are kind of obvious. Machines to make lenses, but also, now that we have computers, machines to design lenses. And it's interesting to speculate now, or not to speculate, but to think back. The graduate students in this room with ZMAX or Code 5 or can design a lens system so complex today with relatively little skill, not knocking you, that it would have taken probably years for people in the 18th century, before the advent of this, using pencil, paper, and logarithms to design. This is a tremendous, tremendous advance in machines. Then materials. If you think about it, the main material in optics, the main material is glass. And when we started out long ago, it was the only way you could make a lens. And this lasted for quite a while, lasted certainly into the 900s or better. You had to have naturally occurring material, principally, I think, quartz, naturally occurring quartz. But now we have, I think the Schott catalog has hundreds of glasses. So the lens designer now can choose his glass for the index of refraction, for the transmittance, for the dispersion, and lastly, markets and money. Now, I'm going to ask a question, but the answer is here. But what was the first successful commercial application of optics? Well, it was spectacles, eyeglasses. It came about in the 1200s, 13th century in Italy. It probably started in Italy because Italy had a well-developed glass industry, that they knew how to make glass, and that glass was available. It started, as I say, in Italy. It was a secret specialty. And spectacle makers were skilled people that ground the lenses by hand, and then later on they invented some machines that were hand-driven to make it easier to do, but not necessarily, and faster. The spectacle technology and practice of making spectacles spread into Germany, into Holland, and finally into England. And it's interesting to note that Benjamin Franklin invented the thank you, bifocal glass. So what had to happen to make this available? Well, first of all, it had to be a market, and clearly the market was there. And it's interesting to note that the advent or the invention of microscopes and telescopes came first in Holland from a center of spectacle making. The skilled artisans that could make spectacles were able to grind the lenses for the very early microscopes and telescopes. But then later on, there became a market for scientific instruments. Crude at the beginning, the astronomical telescopes, etc., that again drove the technology to make it better and more available. And then, this is very simplistic, but lastly, for as far as this little section is concerned, the camera came about. And the camera obviously was first a portrait camera. And that drove another whole technology, the market availability of cameras. Now I want to, as an example of what I'm talking about, I want to talk about the Carl Zeiss Company. You all know Carl Zeiss. It was formed in Germany in the mid-19th century, middle of 1800s. And it's interesting that Carl Zeiss was a manufacturing guy. He knew optics, but he was basically a manufacturing guy. And he brought into his company, and another company, he brought in two guys. One guy by the name of Abe, who was an academic. He was a physicist and an optician, a lens designer. And another guy by the name of Otto Schott. And Otto Schott is the Schott of shot glass. And so here you have a beginning of a company with three people that can supply most of the drivers. They had under one roof methods, Carl Zeiss with his manufacturing ability, Ernst Abbe, who was a powerful lens designer, remember, with pencil and paper and logarithms only. And also they worked with Gauss, the famous Gauss. Gauss wrote about optics, and they used his Gaussian optical theories to help them. Materials, Otto Schott, while he was with Zeiss, Actually, he had a separate company that was owned partially by Zeiss in partnership with him. That company, over the time he was working with Zeiss, he formulated over 100 different glasses to give the lens maker designers in Carl Zeiss company a whole library of glasses so they could choose the right index of refraction, the right dispersion, and the right transmission. They had their machines. Carl Zeiss used machines that were extant at the time and also developed other specialized machines that he kept within the company to further the efficiency and the accuracy of making these objects and the instruments. And then markets and money. Just earlier you saw spectacles as a market. You saw scientific instruments as a market and cameras. Well, Carl Zeiss at one time or another did all of those. But he started out with a microscope. And the reason why he started out with a microscope was twofold, I believe. One was that there was a demand for this microscope, a scientific instrument. It had existed. People knew about it, but they wanted better. And he had the designer that really figured out how to make a microscope, and made seminal inventions of microscopy, the design of microscopes, Abbe. And here is a picture of an early microscope sold by Carl Zeiss. And yet today you can buy microscopes from Carl Zeiss that are as good as any place in the world. They're expensive too. Now, Zeiss then went on, because the invention of photography was right about this time. And the old daguerreotypes, you probably have seen those, started this industry. And as that industry grew and demanded better and better equipment, Zeiss got into the business, and he had a lens designer by the name of Petzval, and you probably recognize Petzval from your studies. But Petzval designed the world's best photography lens at the time. And in fact, when I say at the time, this was, I think, probably 1870. It was the best, really, up until the 30s that was available. And it was a simple design, as you can see. Cemented doublet and a doublet with some air in it. But this set the stage for Carl Zeiss to make the finest camera lenses available. And he still makes lenses today. You can buy out of Japan, you can buy cameras, small cameras that have Zeiss lenses in it. Zeiss doesn't make them. They're made in Japan, but they're licensed as a trademark, and he has quality control people in the factory to make sure that the lenses live up to his reputation, to their reputation. Now, let's come forward for a century or so. The next example of what I call the drivers that has to be assembled together to make something commercially successful would be the Polaroid company. Founded by Edwin Land in 1937, Edwin Land was a remarkable person. He invented Polaroid film, etc. But he had a dream, and I believe that Edwin Land had certain characteristics in common with Steve Jobs. He figured out he knew what people wanted, and by God, he was going to give it to them, whether they liked it or not. And he first got into the instant camera business in 1948. It was not a great success. It had a lot of problems. However, between 1965 and 95, Polaroid developed the famous SX70 camera. I don't know how many people have seen these cameras. You probably have seen them in pictures. But this was a tour de force of camera making. It was a camera that you had an eyepiece, you looked at what you wanted to take, pushed the button, waited a couple, 3 minutes, and out came a color print. It was a revolutionary device, and it sold millions of copies. Here's a picture of it, ready to use. Here's a picture of it collapsed. Now think about this. This is a camera that has optics and produced pretty darn good images that you could open up, but you could almost put it in your pocket. And the interesting thing about it is, here is the cutaway of the optics, and I want to point out a couple things here. First of all, the light is coming this way. You look through an eyepiece that had a convex mirror and it focused on where the film was. That showed that was your viewer. But look at this. This is the lens array. It has an objective lens and a couple other things behind it, other lenses. But in between those rear lenses was a focusing adjustment. This focusing adjustment was such that the lenses never moved. That lens assembly was fixed, and the focusing was done by rotating a free-form surface in and out of the light path. Now, that was revolutionary. And the guy that did it was Bill Plummer. Some of you in the audience know Bill Plummer. He's an amazing individual. He was the last employee of Polaroid that worked directly with land. He was a PhD optiker out of MIT, and he was the chief optical engineer of Polaroid. And he put together a group very much like Carl Zeiss that had under one roof access to drivers. And I want to point out to you, some of these drivers were not inherited. They did not exist when Polaroid came on the scene. Plummer invented, and I say Plummer, his group, but his group I don't think was more than 20 people. Help me out here. Brad, was how many? 15? 15 people. Small group. And they invented methods to make this possible to make the SX70. They invented high precision grinding and turning methods, production of free-form surfaces, which we call oftentimes today non-rotationally symmetric A-spheres. He perfected optical injection molding at high volumes. His machines used DEC mini computers to control them. They worked with suppliers to get the right optical molding plastics so that they could mold high precision components at high volume. The other thing about Polaroid that is very interesting is that camera would not exist if they hadn't elsewhere in Polaroid invented the Polaroid film. This was something that was not known before, had to be invented, developed, and produced in high volume to make this successful. And incidentally, you may or may not know this, but the film that they used, it was a series of films, but the last embodiments not only had the emulsions, the color emulsions in it, it also contained the battery. Each film had a battery that supplied the energy for the camera. And you'll see why this is important in a minute. They also had machines. These machines did not exist before Bill Plummer and his people made them. They had a measuring machine. Now this was probably late 70s. By the time this measuring machine came on, had a resolution of 10 nanometers. That's pretty darn good even today. They designed and made it themselves. They had high precision grinding and turning machines that could make these generalized surfaces to an accuracy, to a precision of about 1/10 of a micron. This was all done in one place. And fortunate for them, they did have a market. Now, at the time Bill Plummer was doing this, the market had been explored because I pointed out the first shot was in 1948. But without the markets existing, this would never happen. So you can see my point about drivers. They had to come together in time. Some of them had been known before, some of them had to be invented and made to make this commercial camera. Now this is a picture of the measuring machine, and you can see the mass of this because there's a guy there. This is built out of granite. I think it was called Huey in their lab. I've seen it actually. I was there one time to watch this thing work. It was built out of granite. It had a counterweighted stylus, very 1/100th of a micron precision. That's extraordinary, isn't it? They built their own motors to control the axes. This is a picture of the work station or the work position in one of their grinding machines. Right here is the grinding spindle. This again was a massive machine, about the same scale as this. All these machines were in high, very, very accurately temperature controlled rooms. The grinding spindle, the work was contained here, and this spindle is a grinding dressing spindle. So they would grind in metal, and these were molds for injection molding. They would grind these to a high precision, very accurate. And during the grinding, they would then redress the wheel to conform to the shape they wanted. And this was all done in situ, so they never had to remove the part. The part came out of that machine almost polished. They did do some post-polishing, but it was they had a very, very experienced, skilled chief optician. I saw him once do this to polish a mold. And this was controlled by a DEC computer. This is the shape of that freeform surface that did the focusing. And this is very clever. I mean, this is an elegant solution to a focusing problem. I think it was an 8th order polynomial with I don't know how many coefficients. And these machines could make a mold and measure the mold to an accuracy that they knew what they were getting, and they could mold this out of plastic. And they'd mold these things, and also they molded other optical elements of the camera. This little X here, right there, is where the center of rotation is. And that is very, very light element would move in and out to produce the focus. So it took very little energy to do this. So this whole camera could be run from the battery that was contained in the film. So this is an amazing thing. And I would say, in my view, computational optics would not exist today if it weren't for Bill Plummer and his group. This was an extraordinary accomplishment. And again, like Carl Zeiss, they put together all of the drivers under one roof. And if it wasn't available, they figured out how to make it. So, let's talk about computational optics for a moment. I use Wikipedia. I used it freely in this, this presentation. Their definition, I think, is a good one. Defined as a capture of optically coded images followed by computational decoding to produce new images. And you see the title of Kathy and Dowski's invention was wavefront coding. It was an example of this. But when you think about this, you arrive at the conclusion that this is a systems technology. You have to code something and then you have to decode something. So you can't isolate the coding from the decoding. They have to be done together. Otherwise, you can't do it. So it's a system technology where you have to jointly optimize both the signal processing and the optics, and the image formation of the optics. And the goal would be whatever you are trying to do. It may not be to form the greatest image in the world. It may be something else. But the final image is there to do a job. It may be to look at, but it doesn't have to be. And this then violates the essential guideline of classical optics. You don't necessarily want the best image at the focal plane. I'm not going to dwell on this. You can read it as well as I can read it to you, but I want to make a couple points here. One is, in general, computational optics is very new. Even if you say that its forebearer was what was called the integral camera, which was written about in 1908 by a guy by the name of Lippmann, a Frenchman, incidentally, who had got the Nobel Prize for the invention of color photography. But Lippmann talked about an integral camera, and that's cited in, however you pronounce NG, his paper. The other thing I want to point out here is that forget Lippmann for the moment. The earliest other citations in the top two were 1966 and 1961. Very, very recent compared to 400 years. And even if you include Lippmann, it's only been 100 years before this thing pops into the scene. The other one I want to mention is Georgiev, his paper, which was now known as Planoptics 2.0, and you'll see that's important in one of the products today. Now, what are the drivers of computational optics? Well, again, our old methods. In order for computational optics to exist today, you had to be able to turn out generalized A-spheres, and you had to be able to make them. You had to be able to produce high-precision lenslet arrays, produce and make them in quantity. Both of these came from Plummer. I claim, without lens design software that was available, you could not do this. Now, some people probably argue with me, but I think that the lens design software was a seminal thing to allow computational optics to happen. And then Kathy and Dowski used what was called an ambiguity function to help them design their wave plates. Ambiguity functions were known in radar, but I think the first reference to an ambiguity function was in 1953. So very, relatively recent planoptic theory. You've already seen the papers, and of course, algorithms to do this computation is very, very important, and it's an area that can be developed as time goes on. It makes it a lot less computations, and it's an important driver. Then we have machines. Again, without Plummer, we wouldn't have computational optics. But I also say without the modern computer, we wouldn't either. And in a few moments when we see the stuff that's on the market, you can appreciate the fact that today we have fast, cheap computers, but not only that, we have special processing chips that do things very efficiently, like NVIDIA, the graphic process units that's used in the architectures they're in, that's used in one of the instruments that's on the market. Materials. I think this may be reaching a little bit, but I don't think it is. I think the ability to have a small choice of optical plastics, not a large one compared to glass, but the ability to have that available for the lens designer is probably a requirement here. Maybe not, but it probably is. And I probably ought to mention along this line the technology now that is available to mold glass. That's an expensive technology, but in certain cases it's probably one of the drivers. Then markets and money. I put a big question mark here. And just as an aside, the investment required to bring wavefront coating to market was about $100,000. You'll see in a minute a camera on the market that has $50 million of venture capital behind it. And that's a lot of money. I think you can slice this market business into two parts. One would be, is it a consumer or commercial? And again, forgetting the government. The other would be, is it a market for images or is it a market for sensing? But this question of markets is the biggest driver today of computational imaging, I think. Today we have two technologies available that is in the marketplace. There are other technologies available, but you can't buy anything yet from them as far as I know. One is the wavefront coating, and wavefront coating is a technology that extends the depth of field of an optical system, so that using this you can get depth of field that are much larger, 6 times, sometimes more, than you can get in a classical imaging system. And then the light field cameras or the planoptic cameras, which utilize an entirely different technology. On the market today, there are 3 examples of these. First example is an example of wavefront coating, and as far as I know right now, it's the only example of a product that you can buy that contains wavefront coating. I suspect I'm wrong here, but I don't know of any other. This is a company called Amnis. It's up in Seattle. The device is a flow cytometer used in laboratory biochemistry, pharma labs, to examine cells. This device, as you see here, is the most recent incarnation. The first devices were in the early 2000s. They were big. They cost $300,000 to $400,000 each. This one is much smaller. You can see with the scale of the monitor there. It costs about $100,000 to $150,000, depending on the whistles and bells you get. It contains a channel that has wavefront coating in it that allows the instrument to form an image that is in focus through the entire channel that the fluid flow goes through. So it picks up in focus anything that's in that channel, as long as it's not obscured by something in front of it. I'm guessing the market here probably is 35 to 50 a year, maybe more. I really don't know, but I would guess at about that much. It's a heck of an instrument. I mean, it does everything. This is a camera that came out, and you probably all are aware of this. It came out about a year ago. It's called a Litro camera. It is an example of a light field camera or planoptic camera. As you see, it doesn't look like a camera. It's kind of a box. This is about, I think, 4.5 inches. It has no diddle things you can diddle with. It has one button you push. It's almost like a point-and-shoot camera. You push a button and you capture an image. This image, though, is a funny image in that you can take the image that's displayed on the back of the camera on the LCD screen, and you can then say, I want to look at this object. You may not know where the object is in the scene, but it will be, you can then bring that into focus. So you can, after you capture the image, you've captured everything there is to know about an image. It's very much like, in my view, like a holographic image. All the information has been captured, and with post-processing and a lot of computer work, you can restore, you can get the image in how you want it in terms of where the focus is. You also can stack these up and get an image that has a large depth of focus in one. There's a cutaway of this. It's got a fairly complex optical system. Lenslet array here that's 1080 by 1080, a megapixel, and that's the resolution of the camera, 1 megapixel. This lenslet array fits in front of a micron 5 megapixel detector, and all of this is computers, electronics, and drivers for the display. It's a pretty neat thing, if you think about it. I can take a picture of this room, push a button, and later on I can bring you in focus, or I can bring you in focus, or I can get you all in focus. Pretty neat. However, you're paying $400 for one megapixel. I can buy an Apple iPhone 5 with an 8 megapixel camera for $200. Autofocus, and I think it even has jiggle control on it. Apple pays $18 for that 8 megapixel camera. $18. So the question really here is, what's the market? You got $50 million behind this. What's the market? It remains to be seen. I'm not convinced personally, and if you read the reviews, that some of the reviews say, well, this is a great toy. We'll see. But it's the first one of its kind, so let's don't knock it. You know, there are better things to come. The other computational optic product that you can buy today comes out of Germany. It's called a Raytrix camera, and this is a Plenoptics 2.0 camera. Because it has fewer lenslets than its resolution. The R1, which is the cheapest camera at $4,000, has a 1 megapixel resolution. It's a video camera, runs up to 14 feet per second. Then there's a twin of this that has the ability to go up to 180, if I said feet, frames per second, 180 frames per second. I don't know what that is, probably $5,000 or so. And then they have a R11, has a 3 megapixel resolution, 10 feet per second. It's about $15,000. The 3 megapixel R11 uses a 10.2 megapixel CCD array to get 3 megapixels. This one, R1 and 5, use micron 5 megapixel. The question here is there a market, an industrial market? That's where they're trying to get. And one other thing too is you can buy an array of lenses. And I think these are just commercial lenses. I don't think they're anything special. So you've got on the market today two technologies. One technology that hasn't gone anywhere, and we'll see why, and then the light field cameras. What are the roadblocks? Well, as I said before, they're not viewed with great respect in the marketplace right now. They're looked at as costly with limited applications. The market has got to drive it. There's got to be a market, otherwise this is not going to work. It's dependent on a lot of computer and algorithm horsepower. Growth on this thing is going to have to be better resolution, less cost and less size. And one way they're going to have to get that is you're going to have better manufacturing to make higher density arrays, and maybe arrays with lens that's changing in either in focal length or maybe A-spheres or whatever. In order to do that, we're going to have higher precision diamond turning machines than we have today, and we're going to have those machines under closed loop control. You also then have to be able to measure these things, and that's very difficult today to measure what I believe will have to be available to make these things advance in the marketplace. Wavefront coating is a little different matter. Wavefront coating is hindered because the owner of the main patent, Omnivision, won't license it or won't license it for any reasonable amount of money, so it's stalled in the marketplace. But the patent is going to be over with in about 18 months. And I think that's going to happen, will open up a market. Because if you only want depth of field in your image, that's the way to go. It's cheap. It doesn't suffer from resolution problems like the wavefront, the light field camera, and it's got applications. Hopefully, the IP problem will not limit light field cameras. Quickly, I want to just point out the imaging market is still on resolution fidelity, color fidelity, and cost. And even specialty markets still want good images generally. Does computational imaging fit there, especially light field? I question whether it does. And I question whether even as it develops that there is a marketplace for consumer imaging there. I could be wrong. But if you look at the other market type, sensing, I think there are probably some very good applications. Maybe they're kind of niche markets, but they're still, I think, viable applications. Because you don't ever, generally, you never look at the image. An example, which is not computational imaging, is the barcode reader. I aim the barcode reader and I wait for it to go blink, and I capture the barcode. I never see the image, never. And not only that, the algorithms are such that the image can be very badly blurred, out of focus, and it will still capture and decode it. So where does computational and sensing fit? I think it does have, I think it has future there. And the future is this. If you can overcome the resolution, size, and cost limitations, and you can probably with better machining, metrology, and computing, then I think you can get into the industrial markets, gauging as an example, machine vision, 3D applications. The light field camera is essentially a 3D device, and it will pop out a depth map with the right software, which has a lot of application in the future. Security, if you can, the present cameras are limited because they focus generally very close. If you look at the pictures that are available on the web, they're not 10 meters away. They're about 1 meter away. One reason is that the object lens is the diameter is very little. Consumer market, again, we've talked about that. Wavefront coating has a lot of future applications, I think, once the IP is settled, the patent expires. Because if, as I said before, if EDOF is the goal, that's the way to go. There are some other technologies I'm just going to brush across that are not on the market, but are promising. Non-focal plane cameras, non-planar focal plane cameras with many small cameras, somewhat like you saw the Brady camera last week. I think we'll once some precision problems in machining and assembly are overcome, probably we'll have a commercial market. The thing that fascinates me is there such a thing as a light field projector? And if there is there a commercial demand for it? I don't know, but I'd say stay tuned. And then there's some sparse pixel applications which are kind of like optical flow. Well, they're optical flow technology that I think will come about. So, that's it. Thank you. Yes?
Do you consider digital holography or auto-focusing systems as computational digital holography?
Digital holography? Well, I think the light field camera perhaps is a better solution because
I mean, it's commercial.
yes, in a limited sense. Oh yes, yeah, that's exactly right. But I really don't classify that as computational optics in my sense. I'm not arguing, but it's not exactly what I think we're talking about. First of all, most of that, this just an aside, most of this is, or all of this we've been talking about is non-coherent. Yes?
How comes that Carl Zeiss is still flourishing? Everybody knows about it, and Polaroid is well gone.
Well, I'll give you a personal opinion. It's management. The demise of Polaroid was the fact that when Edwin Land left, idiots ran the company. And they ran it into the ground, literally. They ran it into the ground, and it was an example, very much like Kodak, that they just could not keep up with the times, and they could have kept up with the times, I believe. But Carl Zeiss always kept up with the times. And the other thing is that Polaroid, I believe, and I'm not sure of this, did not have was not willing to bet the ranch, to put a lot of money behind it. Carl Zeiss had put millions of dollars into lithography lenses, for instance. They have, over the years, been putting lots and lots of money into developing the drivers they need. And you know, it's the same, much the same story that companies get wed to what they were successful at. In fact, you know, the whole history of the semiconductor device is the fact that today there are no semiconductor device manufacturers that have ever manufactured a vacuum tube. It's a hard thing to answer, but it's true. Well, a great example of another company that doesn't fall into that is IBM. IBM has reinvented itself time after time. And a lot of their competitors are no longer there. Why? I think they had good management. Yeah.
What can you say about the pace of adoption? So we've got, you know, most of the people in this room have lived through an era of, you know, version 8, 9, and 10 of any given technology, right? But you're talking about centuries of using glass. And it seems to me that the use case hasn't changed dramatically enough to change that technology. We've got tools around it, but optics as an adopted technology has taken an awful long time for consumers to get comfortable with.
Well, I think that's true, but I'd also say you have to ask yourself what consumers. For instance, the lithography business has been pretty rapid, and has forced pretty rapid change on optics. That's an example because the demand was there. You know, early on people figured out if I can cram more devices into a wafer, I'm golden. I can make lots of money. But I think you're right. In general, what you say, it's a slow-moving thing. However, I think this stuff has a chance of moving a little faster. But you see, one reason why it's slow-moving are these drivers. You have to have things in place to make the next jump. And today, you don't have, with one exception, well, a couple exceptions, you don't have companies that are so integrated that can do this all under one roof. Apple doesn't make their iPhones or their devices, period. They don't have control over the machines. They may, or the manufacturing methods. One exception I would say, which is going to be interesting to look at, is Google. Google has a lot of work in computational optics. Google, Adobe, Microsoft, those are some of the people that have, and you don't hear about that too much. Adobe publishes quite a bit. This Georgiev has a lot in the literature. But that's a good question.
You know, I just think it's interesting. We're all beneficiaries, especially if we have a phone. We've got LCD, camera, digital chips. They're all beneficiaries of optical technology.
One way or the other, that's right.
Right. We all use it. But our adoption of base optical technology has been slow.
Slow.
As consumers.
Slow change. The technology doesn't change that fast. That's right. Yeah.
So, given that the United States is losing most of its manufacturing capability, you can't even in this country have all the elements that are necessary under one roof in the country. We've lost so much.
I debate that in only one way. That is, it's a matter of scale. You're absolutely right if you think about the cell phone. We no longer can manufacture in mass. However, if you think about something like that Amnis, or things that are much more limited marketplaces, then I think we have a good shot. You know, where's the cutoff point? I don't know, but it's probably somewhere between maybe 100,000 units a year and perhaps twice that or so before you have to go overseas. But you're absolutely right. But the other thing is, you see, what makes it difficult, again, if it's a small market, typically you don't have big pots of money to bring these together like Zeiss did or like Polaroid did. It's a vexing problem. Yeah.
Well, maybe you'll, but what happened with wavefront coding at Omnis?
Well, very simply, the thing that happened was they bought our company. They told us, oh, we want you to go ahead and work, go on with wavefront coding. All of a sudden said, no, we're not going to do that. And they refused to license it to anybody that would, for a reasonable amount of money. We tried to license it. And they came back and said, well, we're glad to license you for an upfront of $250,000 for each application. I mean, ridiculous. So it just you know, turned the valve off. Now, as I say, 18 months from now, that valve is going to be gone. So we'll see. It's a shame, I think, a real shame. Yes?
So, there's questions of whether software patents are going to be around much longer. Do you think that the patents in this area have been a driver for the industry or more of a hindrance?
Well, I can't speak for software patents. That's beyond my capability to understand or competence to know. But I think in certain areas, yes, IP has been very, very powerful. Well, look at the Apple Samsung trial that just ended. You know, that was a couple $2 billion. An interesting historical fact. Polaroid and Kodak. Kodak finally, after Polaroid showed that there was a market for instant imaging, Kodak got into the action and started making instant cameras. Polaroid sued them and won and required Kodak to literally scrap, mechanically demolish $1 billion worth of inventory because they violated their patents. IP is still very powerful today, and I think it will be. About software, I don't know. I can't answer that.
Okay, there are no more questions.